Hello everyone, I am Indrajyoti Gaine. I am a PhD student at Department of Mathematics and Statistics at IIT Kanpur, and presently I am a PMRF fellow, and I have cleared CSIR NET with 108 rank. Okay, so in the last class we were discussing about relations, and we came up with the definition of Cartesian product. So we have discussed one Cartesian product, which was defined by A cross B, where A and B are two non-empty set. Next, we have defined relation. Okay, so relation were nothing but the subset of A Cartesian product B. Okay, so that thing we have discussed in the last class, and also we have discussed about what is the domain, range, and codomain of the relation. So, for example, take one example today so that it can be clear. Okay, so let us define the relation R is the collection of all those x and y such that y equals to x plus 3. Okay, so also we have discussed this kind of problem in the last class, but today also we are discussing the same problem to clearly understand the problem. So in our last class we knew that A was the set 1, 2, 3, 4, 5 and 6, and this R is subset of A addition product A. That is R is a relation on A. That is, we can say that R is a relation on A. Okay. Now let us find the domain, codomain, range of all these things. So what are the elements of this relation? So clearly you can see this is the set builder form of relation. So this is the set builder form of relation. This is called a set builder form. And similar way we can write the roster form. So let us write the roster form of this R. And in the roster form we can find the elements R equals to, in second bracket we can have x equals to 1, then y equals to 4, x if 2, then y is 6, if x equals to 2, then y equals to 5, not 6, and whenever x equals to 3, y equals to 6. So except these three elements, we can't have many other elements, because if I take x equals to 4, then y equals to 7, and 7 is not in A cross A. That is 4 comma 7. The element 4 comma 7. This is not belongs to A Cartesian product A. So we can't take this element or further elements. Okay, so we will end at this point. So if I point out what are the domain of this relation, so domain is domain of R is 1, 2, 3. What is the image of R? Is not image of R, that is called range of R. Image is of an element, that is 4 is an image of 1. Here we can write 4 is image of 1, 5 is image of 2, and 6 is image of 3. Okay, so we can write this and we can put it in separate line so that, yeah, okay, like this. So we can make the change the color also. Okay, can we change or not? Yeah, okay. Okay, so yeah, and what is the range of R? Range of R. This is the set 4, 5, and 6. Okay, so this is the range of R. This is the domain of R. And what is the codomain of R? Codomain of R, that is the set 1, 2, 3, 4, 5, 6. This is the codomain of the relation R. That is the whole set A. That is the whole set A. That is, we can understand that whenever we have a relation. Suppose we have a relation R, which is A cross B, subset of A cross B. Then the codomain must be the set B. Codomain must be the set B, and but the rest of the thing like domain and range, that can be seen from the relation on how a relation we have defined. Okay, so we have discussed these things, and one remark is that you can clearly see from the above that range is always a subset of codomain. Okay, this is subset. Range is a subset of codomain, and it is obvious because of we are taking the elements from the order pair from A cross B, so it must be happen. Okay, so let us take one example of relation. Okay, before going to the example, we can define this relation. Whatever we have done here, we have taken a relation A from here to here, and we took all these things and we define the relation here, right? Now, how can I see the visual representation of this relation, or just by visually, how can I represent this relation? So for that, we can define like this. This is the set A, which is our domain, not domain. This is the set A, and domain is a subset of this set A, and this is our codomain set, which can be B. But in this case, this is our A. So both are A. This has element 1, 2, 3, 4, 5, 6. And this is element 1, 2, 3, 4, 5, 6. So by what are the elements of the relation? 1, 4. That is, we are sending 1 to 4. We are sending 1 to 4. Then we are sending 2 to 5. We are sending 2 to 5 and 3 to 6. Okay, so thus we can define a relation, and by this arrow we are denoting that this is our P-image, or we can say the element of the domain, and this is the image of the pre-image, that is image of 1. Okay, so by this process we can visually represent a relation. So let us take one example that is also given in your book. So we have a figure. First of all, we have a figure. That is a visual representation of a relation. So we have the points 9, 4, and 25. And in this side, we have the points 5 3 2 5 3 2 1 minus 2 minus 3 minus 5 1 minus 2 minus 3 minus 5. Okay, and we have a relation from here to here to here, then here to here, here to here, here to here, and here to here, here to here. So this is a very one important example of relation, and this will we need this example further in the next section before going to the function. So please recall this function, recall this relation. Okay, so the question is, write this relation in set builder form, in roster form, and what is its domain, what is its range, and what is its codomain. So codomain set is this YOLO set is codomain set, obviously. Codomain set. Now the question is, what is the relation in roster? In at first of all, we can write it as a roster form. The roster form is like 9 comma 3, 9 comma minus 3, 4 comma 2, 4 comma minus 2, 25 comma 5, 25 comma minus 5. This is the roster form of this relation. What about the state builder form? So you can clearly see this here, that 3 square equals to 9, minus 3 square equals to 9, 2 square equals to 4, minus 2 square equals to 4, 5 square equals to 25, and minus 5 square equals to 25. So here we can write this as a set builder form, like collection of all those x and y, such that x equals to y square and x equals to 9, 25 and 4. 9, 25, 4. Or we can also write this as a set, and x is belongs to the element this, and this is our set builder form. Perfect. Perfect. Okay, then what is the domain of this relation? Domain is the set 9, 4, 25, and what is the range of this relation? Minus 2, minus 2, comma 2, 3, comma minus 3, 5, comma minus 5. So this is the range of this relation. Okay. Now, one question, that in the last class, when we have defined the Cartesian product, we could found the element of Cartesian product, like how many elements the Cartesian product have. Okay. So if, okay, let me write first. So if A and B are two non-empty set, are non-empty, and if number of A equals to P, number of B equals to Q, then number of A cross B was PQ. Okay. Now the question is how many relations are there from the set A to B? This is the question. Okay. Now observe one thing, that any relation is a subset of the set A cross B. So note that relation is a subset of the set A cross B. Okay. Now, from our previous knowledge, we can recall that how many subset we can have of the set A cross B. So the number of subset of the set A cross B was 2 to the power PQ. Why 2 to the power PQ? Because number of elements in A cross B is PQ. And we know the cardinality of power set of A cross B. This is nothing but 2 to the power PQ. And a relation is nothing but an element of the power set. Right? Because relation is subset. So relation is nothing but an element of power set. So that how many relation we can have? That is nothing but the cardinality of power set. Okay. Therefore, we can have at most 2 to the power PQ many relations. Okay. Now come to the next section, that is called function. Functions. Now I will come back to function little later. Before that, come to this example. Just observe one thing. Okay, observe two difference between these two examples. So first of all, state one statement. First of all, statement before that. A function is nothing but a relation. Is nothing but a relation. Okay. So put this in your mind and then think about these two relations. Okay. Now observe these two relations. What are the difference between these two relations? And can we say these two are function or not? Okay. So let us see that in the second case, can write it in green, it will be easy to understand then. In the second case, 9 has two images. 9 goes to 3 and 9 goes to -3. How we have defined a relation? We can have two images of 9. Similarly, 4 has two images. 4 goes to 2 and 4 goes to -2, right? Similar way, in the first example, this example, you can see 4, 5, 6 has no image. Okay, so there we can see in these two relations there are some drawbacks. In one case, few elements have no image, and in one case, all elements have image, even multiple images. One element has multiple images. So we are defining function to those relations like this. So let us state the definition of function. So a relation from a set A to the set B is said to be function, is said to be function if every element of A has one and only one image. One and only one image. One and only one image. So highlight two portions of this statement. That is, every element of A. The first portion is this, and second portion is this, one and only one image. So these two portions are very important in the definition of a function. Definition of a function. Why? See, in these two relations, in the first case, we don't have image of all elements. We don't have the image of 4, 5, and 6. And in the next example, we have two images of 9, 4, and 25. Yes, in this case, we have all images of all the elements in set A, but we have extra images, like one element has two images. That is not possible for the definition of function. So in general, we can understand one thing. We can recall the definition of function. One person can have only one mirror image. So if I see in a mirror, I will look same as I can see myself in another mirror. Okay, so that is the thing. A person can have only one image. This is not possible that a person has 2, 3 type of image. Yeah, in the society, one person have 3 type of image or 4 type of image, but in the mirror, he have only one image. Okay, so in the case of function, must recall that every element of the set A, I mean the domain set, must have only one images, one and only one image. So by this definition, these two relations are not function. Let us define a function of an example of a function. So they define if from R to R defined by f of x equals to 2x. Okay, then what are the elements of this? No, not like this. We can do different way. If from natural number to natural number, it will be more convenient. But in case of real number, it will be difficult to see every element, so it will be easy. So in this case, what is our a? A is nothing but natural number, and it must be a natural number, and this is nothing but a domain. So in case of function, the domain must be the whole set. It cannot be a subset of the n. I mean, wherever we the defining the function, the whole domain will be considered as the a. Okay, so a equals to n. And what about the set range? Range of this function or relation is the 2n. Why 2n? 2n means we are multiplying each element with 2 and we are collecting all these elements. Like this is the collection of all those 2n. 2n as that n belongs to natural number. Okay. And what is our codomain? Codomain is natural number set. Okay. Now what about this function? And okay. Yeah, so this is a function. Why is this a function? Check that whenever if x1 and x2, x1 equals to x2. Suppose x1 equals to x2. This is the condition x2. Then this can imply 2x1 equals to 2x2. Right? 2x2, which implies f of x1 equals to f of x2, right? So we took this and we obtain this. So this is called the well-defined function. So thus we can check if function is well-defined or not. Thus we can check that a function is well defined or not. So thus we can define the function is well defined or not. Well defined means that function is we can define the function or we can call it as a function. This is the meaning of well definedness. That we can call this relation a function. Okay. Okay. So by this process we can check that the function is either well defined or not. So we pick any two element from the domain and we will check that the images are equal or not. Okay. Okay. And if we have this, like if this doesn't imply this, then there are some glitch and we cannot say that it is a function. So we must imply this to say that it is a function. So this is called a well-defined condition. And obviously this x is called pre-image and this 2x is called the image. This is called image and this is pre-image. This x is called pre-image. Okay. Okay. So let us take another example and we get to find that those are relation or not. So the question is, if the following relations are function or not. So the relations are 1, 2, 1, 3, 1, 4, 2, 2, 1, 3, 1, 4, 2, and in the case of 2, 2, 2, 2, 2, 2, 4, 3, 3, 4, 4. So see this, in the first case, all the domain has exactly one images. One the elements of domain has exactly one images. So this is a function. But in the case of 2, this element has 2 image. 2 has 2 images. 2 goes to 2 and 2 goes to 4. So this is not a function. I hope this is clear till now. Okay. Now we can define how can I draw a graph of a function. Okay. So let us start with an example. The example is this one. F is equals to 2x. F from R to R. Let us define F from R to R such that F is equals to 2x. So how can we plot this graph of the function? So this is our R2 plane. We must put arrow because this is infinite. This is our x-axis, this is our y-axis. Okay, and y means y equals to f of x. Okay, so this is our 1, 2, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, and so on. This is 1, 2, 3, 4, 5. This is minus 1, minus 2, minus 3, and so on. Okay, so we are going to draw this graph of the function 2x. Okay, so whenever it is 1, for x equals to 1, the value is 2. So the point will be here. X equals to 2, the value will be 4. The point will be here. When x equals minus 1, then the value will be minus 2. Value will be here. And when the x equals to minus 2, value is minus 4. So value will be here. So you can clearly see the line will be like this. Okay, when x equal to 0, then 0. Obviously 0. So this is the graph of the function 2x. Now we can check that what about the x equal plus 3. X, okay. What about the function g? G goes to R to R such that g of x equals to x plus 1. So again check this by plotting the graph of the function x, and this is our y. 1, 2, 3, 4, 5, 6, minus 1, minus 2, minus 3, minus 4, minus 5, 1, 2, 3, 5, minus 1, minus 2, minus 3, minus 4, minus 5. Okay, let us draw this problem. So whenever x equals to 1, y must be 2. X 2, y is 3. X 0, y is 1. X minus 1, y is 0. X minus 2, y is 1. So the line will be like this. Joining all these points, we can draw the graph of the line x plus 3. Okay, so what we are doing? We are just finding some particular points and its images, and by these points plotting, we are guessing what can be the graph of the function, and thus we are drawing the graph of a function. So that we can draw. Thus you can draw the graph of functions. Okay. Now let us see some few example, few kind of functions, special functions, and these are very much important functions. So first of all is identity function. So by the name we can clearly see the function is from some domain to some domain, and the function will be some if x equals to x. If x equals to x. Okay. So the graph will be like this. This is the graph of the function. Y equals to no. This is the graph of the function. This is our x-axis, this is our y-axis, and this is the y equals to x line. Okay, y means f of x. Y means f of x here. Next one is constant function. Constant function. So the function is defined like f from R to R, defined by if x equals to c, where it is for all x in R. This is for all x in C. I think you are familiar with this notation. This notation stands for all. For all means all x belongs to R. We can see if x equals to C. Now what is this C? C can be any constant number. It can be 0, it can be 1, 2, 3, 4, 5, and any constant. That is, this C can be changed. This is fixed for all points. So what will be the graph of this function? So graph of the function will be like this. This is our x, this is our y. Suppose that C is here, so the graph will be like this. X equals to C. Or we can say this is equals to C. This is the graph of the function. Next example is polynomial functions. Polynomial. So polynomial function is a function f from R to R, defined by f is equals to a0 plus a1x plus a2x square and so on up to an x to the power n. This is called a polynomial function. So clearly you can see where x is a variable, x is varying over the set R for all x belongs to R. So x is varying over the set R, and coefficients of these terms like a0, a1, a2, a3 and an, these are scalars. I mean, these are fixed constant numbers. We can't change this. Yeah, we have to choose this first, and according to our choice, we will get a polynomial function which is of the function of x, and this will be of the form this. Observe that this n must be a natural number. N must be a positive integer, or you can say natural number. Okay, so positive integer is nothing but natural number. So yeah, n must be a positive integer or natural number. Okay, here n is natural number. So let us see two example. One example is f is equals to x cube minus x square plus 2. This is a polynomial. What about this? F is equals to x to the power 3 plus 2x minus root over 2. This is also a polynomial. What about this? X cube plus root 2x plus 5. So here we have taken the coefficient 5 minus root over 2 and here 1. Right? So this is also a polynomial. Now check. F is equals to x to the power 2 by 3 plus 2x. So obviously this is a function, but this is not a polynomial. This is not a polynomial. Why this is not a polynomial? Because in this case the power is not a natural number. This is not a natural number. Not a positive integer. 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 So this fact implies that this is not a polynomial. So this is not a polynomial function. Polynomial function. Okay. So thus we can define what is polynomial function. Okay. Okay. So now these are few examples of special examples of the functions. Now we have rational functions. We can have rational functions. Fourth one is, so before the proceeding further, you can ask that why we are not making a graph of this function. So this is a sum of few monomials. We can say this x square, x cube, these are monomials. So each monomial has separate different graphs. Now whenever we are combining with some weightage like a0, a1, these are some weight on the monomial, then it is difficult to draw a polynomial without knowing the value of a1, a2, a3 and so on. So in general, we can draw some few graphs of monomials, and we can understand that these are nothing but, if we write a polynomial and we can draw that we want to draw some graph, it will be a similar kind of function, or it will be combination of all these functions. Okay, so let us draw the graphs of the few functions. Like this is the graph of y equals to x. We have already seen this thing. This is our x axis, this is our y axis. So what about the function y equals to x square? This is x, this is y, and this will be the graph of the function. This is y equals to x. This is y equals to x square. Now, if I draw the graph of the function like this, you can check these things by plotting the points, and how we have discussed this thing here. You can check all these functions are coming or not. So this is the function of y equals to x cube. Y equals to x cube, and you can clearly see that all these points are passing through the point 0, and if we put x equals to 0, then we get y equals to 0. this region with this function is passing through the point 0, and so on. Thus, we can draw all the functions, and combining all these functions, we can get the graph of the polynomial. And depending on the coefficients, it may be happen that a1, a2, a3 are 0. Like in the case of x square, if I draw this x square graph, then there is a0 is 0, a1 0, a2 can be 1, and others are also 0. By this process, we can get these functions and we can draw these graphs of the function. Okay. So thus we can draw the polynomial function. And next one is rational functions. Rational function. So rational function is a function of the form fx by gx, where the function gx is not equal to 0 for all x of the set domain. D stands for domain of the function. Okay, the rational function is the form this. So one example of rational function. So let us define a function f from minus 0 to r minus 0, because we don't want to include that point because we however define the function. So the function is f equals to 1 by x. You can see if this 1 is one function and g is, and this x is another function. So we are writing this as a ratio, and this is our rational function. Okay, and we are excluded 0 because if we put x equals to 0, then 1 by 0 it is an undefined number. So we don't want to include that point. That's why we, in the domain of definition, we reduce the point 0. So this is the domain of the function. So depending upon the function, we can define what is the exact well-defined domain for the function. So if I draw the graph of this function, what it will be? It is a very interesting thing. If I draw this graph, it is our x-axis, this is our y-axis. 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5, and so on. If I put x equals to 1, then 1, x equals to 2, then 1 by 2, x equals to 3, then 1 by 3, and so on. If I put x equals to half, then it is 2. X equals to 1 by 3, then it is 3. Like this. So the graph will be somewhat similar to the function like this. Okay. And what about this? When we see minus 1, then minus 1, minus 2, then minus half, minus 3, minus 1 by 3, and if I put equals to minus half, then it is minus 2, so on. So this graph will be similar kind of like this. Okay. So this is the graph of the function 1 by x. So in the positive direction, it will be going up direction, and in the negative direction, it is going to the down direction. And this is one example of rational function, and that's why you can see that at the point 0, there are still, the function is not defined. Okay. So this is the function graph of the function y by 1 by x. Okay. So thus we can define the function. Next one is modulus function. What is the modulus function? Modulus. So this is the function defined like f from r to r, defined as fx equals to mod x. And if I draw the graph, mod x is always greater than or equal to 0. So it will be very easy to draw this graph. X and y, we are not drawing the negative y-axis because we don't need, because of this function defined here. Mod x is always greater than or equal to 0, similar as x square. X square is always positive. You can see the graph of the function is never going to the negative y direction. Similar way, here also the function will not go to the negative y direction. So if it is 1, suppose this is our 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, this is 0. So x is 0 at the point 0, 1 at the point 1, 2 at the point 2, 3 at the point 3, 4 at the point 4. This is here. What about minus 1? Minus 1 is 1, minus 2 is 2, minus 3 is 3, and minus 4 is 4. So this is the graph of the function y equals to mod x. Okay, clearly you can see these points. This is 3, 3, and here it is minus 3, 3. Similarly, minus 2, 2, here it is 2, 2, like this. And thus we found the graph of the function mod x. Or we can write this function as like this: f(x) equals to second bracket x if x greater than equal to 0, and minus x if x less than 0. Okay, and also like this we can write this modulus function. And the next function is signum function. The fifth one, sixth one is signum function. R to R defined by f(x) equals to 1 if x greater than 0, 0 if x equal to 0, and minus 1 if x less than 0. So this is nothing but combination of three constant function. Like whenever the function is defined over negative real numbers, function is constant minus 1. Whenever the function is defined on the point 0, it is equals to 0. And whenever it is defined on the positive real axis, then it is plus 1. So what is the graph of the function? This is y, this is x-axis. So at the point 0, it is 0. Let us draw this with green line, green, okay, yellow point. So at the point 0, it is 0. At positive axis, it is 1. So the graph will be like 1. And negative axis, negative x-axis, it will be minus 1. Okay. This is our points 1, 2, and so on. This is minus 1, minus 2, and so on. Okay. So this is our signum function, and this is the graph of the signum function. So, or we can write this f(x) like this: f(x) equals to mod x by x. So clearly you can see that whenever x is greater than 0, if x greater than 0, then f(x) equals to x by x, which is equals to 1. If x equal to 0, then f(x) equal to 0. Why? Because mod x equals to 0. Then mod x equals to 0, so f(x) equals to 0. And if f(x) is if x is less than 0, then f(x) equals to minus x by x, which is equals to minus 1. But in this case, we can get some confusion. In this line, we can get some confusion. So it's better to write this as this function. It's better to write this as like here. Okay. The signum function can be written like this. And the last type of example is, it is important for you also, the greatest integer function. the sixth one, and the seventh one. Greatest integer function. So what is the function defined as? From R to R, defined by is equals to box 6. Box 6. And what is a box 6? This is nothing but the greatest integer less than x. What is that number? Suppose, just take example. Suppose we are finding half. Now, what is the greatest integer less than half? So, less than half, the integers are 0, -1, -2, and so on. So what is the greatest one? Greatest one is 0. Similarly, what about 1.5? That will be 1. What about the function 2.3? That is 2. This we are finding the all. We are first of all we will see all the integers which are less than 2.3 or given number. Then we will see the maximum. That's all. So in case of this, what will be the graph of the function? The graph of the function will be like this. It's very interesting. X and this is Y. So we will find 1, 2, 3, 4, and so on. -1, -2, -3, -4, and so on. So this will be this will looks like we can draw it green line. We are not including 1 here. Check that 1 in the next lot, and we will stop before 2. Again 2 is in the next, and we are stopping before 3. Again 3 is in the next, and we are stopping before 4. So note that box 4 equals to 4, box 3 equals to 3, less than 3, greater than equal to 2, then box 6 equals to 2, right? And that's what we are doing here. We are not including. So you can see in the book they are using this condition, this kind of hole. This hole means we are not including that point. There is an open. That is open. Right? So thus we can define the graph of the function. Graph of the greatest integer function. Okay. So today we have discussed all the definition of function and all kind of function, or not all kind of function, few interesting kind of functions, and how to draw their graphs, and which are function, which are not a function, all these things. So in the next class we will discuss some algebraic relation among the functions, and next we will see some few more examples about the function relation and Cartesian product. Okay, so we will end here.